Hi, and welcome to our conversation today on acid-base indicators. Most acid and base solutions are clear and colorless. So if we're going to add an acid plus a base and discover when we have exactly equivalent amounts of each in terms of moles, okay, moles of acid, moles of base, or more specifically, moles of H plus and moles of hydroxide. Um, we need some way to see that because we have a colorless acid, a clear and colorless base, making typically a clear and colorless salt solution. So we need to find a way to indicate or to show us when that equivalent amount has been met. So what we call that, what we want to use is we want to use an indicator. An indicator changes color at that equivalence point. Okay, now when the indicator changes color, we call that the end point. So if we're going to do a titration is when you slowly add a titrant into an analyte, and when those are equal, we have an equivalence point. If we add an indicator, our goal is that that indicator changes color as close to that equivalence point as possible. So you want that end point to be as near the equivalence point. Those are not the same terms. That's why I'm saying them a few times to help you get that kind of straight. Okay, now indicators change color with pH because they change structure with pH, and structure determines function. Now, the changes are a little bit more complicated than a typical protonation, deprotonation occurring in an acid and a base. So you notice here you have the hydroxide and it becomes a double bonded oxygen. And then do you notice here this bond here, it's kind of this trickle, actually would be going that way, movement of electrons, and that becomes broken. And then this one happens to have 2 points at which it changes color. It goes from red to yellow with the first structural change, and then yellow to blue with the second structural change. So it's a little bit more complicated, but it still fulfills our purpose. Changes with pH, and that's what's important. So let's take a look. Let's delve a little bit more deeply into how that happens. What we're going to be looking at is an indicator whose pKa, so that's minus the log of the equilibrium constant, is as close as possible to the pH of the equivalence point. Now, we can look at that in a little bit more detail, but I want to simplify things a little bit. Okay, just get myself a little bit of room. I'm going to use a simpler notation for my indicator, and I'm going to use HIN. So that just means the protonated form of the indicator. And then we have water. So I'm writing effectively the acid-base equilibrium for this. So very simplified. And H3O plus. Now, if I wrote the Ka for this, Ka is the acid dissociation constant, the equilibrium constant for weak acids. It would look like this. Okay. Okay, just, whoops, it's a lowercase, but you get the idea. Okay, let me fix that for us so you don't get confused in the process. Symbols have meaning, I tell my kids. Close enough isn't good enough. Okay, so this is the protonated form, and this is the deprotonated form, sometimes called the modified form. You should understand those terms. Protonated, so this is the protonated with the proton, and this is the deprotonated form without the proton. or modified form of this. Now, what scientists find, is that the color change happens when my concentration of that deprotonated form gets large enough that our eyes can see the color change. And there's a range at which that happens. And so if we look, what we're going to do is we're going to zero in on this ratio because that's our colored portion of this. So what we find is that if that ratio of indicator deprotonated to protonated form is greater than or equal to roughly about 0.1 to 1. So we have a range of 10 to 1. Okay? So if I plugged those values into there, my range would be when I have a Ka on the order of 0.1 times my H3O plus, so that'd be one end of my range, and then I'm going to put the 10 in there, that 10 to 1 times my H3O plus. All right, now we tend to like to look at pH, so if we wanted to compare this to pH, we have pH would equal the pKa plus or minus 1. Okay, so pKa is minus the log of our Ka. Right? So that's our take home here. That gives us the range of when we would be able to use an indicator here. Okay, so you want the pH of the equivalence point very close to pKa. So this would be your pH of your equivalence point. All right. So let's take a look at an example. And this is where knowing how to do a little bit of an estimate would help. So I have an acid dissociation constant for methyl orange. So if I take minus the log of 2 times 10 to the minus 4th, this could be a multiple choice question. And much like we did with pH, we can estimate, we can look at that power. That power is a -4. The font's a little small on this to give me more room to write. Sorry about that. So it's 2 times 10 to the minus 4. Therefore, my pKa must be approximately 3 point something. So you look at that power and you go down by 1. So it's right in that range because I've got plus or minus 3.65. So it's going to be right in that range of the plus or minus 1. So that would work well. Okay, another thing you can do is there are charts of indicators that are really handy. Quick Google image search and you're going to find charts that show those colors of your indicators and over what pH range they will change. So depends on the context of the question or if you're in a laboratory situation, what you're going to want to use. But all right, thanks for joining me. I hope this helps you in your journey of learning some really awesome chemistry. Take care.